Hello, my name is Giovanni Guizzo. I'm a research fellow at University College London, and today I'm going to present to you the paper Sentinel, a multi-objective hyper-heuristic approach for the automatic generation of mutant reduction strategies. So if you're watching this presentation, then you might already know about mutation testing, but I'll start with a quick overview of the topic, just to recap. Basically, you have your original program, you apply mutation operators that synthetically change the code, and then you generate a mutant, which is a buggy version of your software. The objective is to create test suites that can kill those mutants. To kill a mutant, one must execute the test case against the original program and the mutant program, and if the output of both are different, then the mutant is said to be killed. The more mutants you kill, the higher your mutation score. The greater the mutation score, the better your test suite is in reviewing the faults represented by those mutants. However, running potentially thousands of mutants against multiple test cases incurs a great cost that still hinders the adoption of mutation testing in practice. There are two main types of cost in mutation analysis: the manual cost of assessing equivalence and the computational cost of generating and executing mutants. In this paper, we focus on the computational cost. In order to reduce the cost of mutation testing, there are several mutation strategies that can be used. Some of them are called do faster strategies, which basically try to execute mutants in a faster way, such as using parallelism, bytecode mutation, and other methods. There are the do smarter strategies that avoid the total execution of a mutant, for instance, weak mutation or checkpoints in the execution of mutants. And then there are the do fewer approaches, which execute fewer mutants, because by executing fewer mutants, the cost of executing them is also reduced. So they do this by selecting mutants or discarding operators. The general idea here is to reduce the cost without affecting the mutation score. However, there are some limitations with conventional strategies. First, there is no strategy that is universally the best in all scenarios. To make things worse, there are so many strategies to choose from and so many configurations that the engineer might get lost. Hence, the engineer must experiment with the possible options to decide which strategy better fits their needs. Another issue is that the strategies are too general. Specialized mutation strategies are necessary to cater for the specific needs of a company, project, or the engineer. But the question here is there a way of automating the discovery of such strategies to perform mutation testing in a feasible time without losing effectiveness? This is precisely the objective of our work. For this purpose, we propose Sentinel, a hyper-heuristic that generates specialized strategies. But before talking about Sentinel, let me introduce to you hyper-heuristics. Hyper-heuristics act on the heuristic space rather than problem space. In other words, hyper-heuristics search for the best heuristic to solve the problem, instead of trying to solve the problem directly. So, hyper-heuristics, they do not search for a solution. They instead search for the best heuristic that can, in turn, search for the best solution. So, hyper-heuristics can select existing strategies or generate new ones from existing components. Also, hyper-heuristics can learn online by self-adapting or search for heuristics beforehand for later reuse. With that in mind, instead of using a general heuristic to try and kill mutants, we created an evolutionary hyper-heuristic that can create mutation heuristics that in turn can kill the mutants for us. Well, the advantage: the output is a specialized algorithm that's fine-tuned to the program we are testing, considering both cost and quality. How does Sentinel really work then? Well, it first receives as input a grammar with all the rules needed to build the strategy, dictating how the building components can be placed together. Then the solution in a low-level representation goes through a translator to decode it using the grammar into a full working strategy. Then, this strategy is executed to generate and select mutant. Those mutants are in turn executed against the test suite, and we finally obtain the results in matter of cost, in this case execution time, and the mutation score. This result is fed into the training process over multiple iterations, and the hyper-heuristic stochastically produces similar strategies to the best one so far, with small deviations. In the end, the best strategy are outputted as possible mutation strategies for the system, and then the engineer can reuse those strategies to test their software. as per usual, we performed a set of experiments to assess the effectiveness of Sentinel. We used 10 real-world systems in the comparison and the pig mutation tool to create Mutant. We have also included 3 traditional mutation strategies: random mutant sampling, which selects mutants at random in a given percentage; selective mutation, that leverages operator information to select only the most relevant mutation operators to perform the mutation analysis; and random operator selection, which selects only a subset of random operators. For the research questions now, we are concerned into answering whether Sentinel is better than a random hyper-heuristic in research question number 1. In research question number 2, we compare the traditional strategies to the ones generated by Sentinel. And finally, in research question number 3, we check whether the strategies lose their effectiveness over time, and whether we need to retrain Sentinel in newer versions of the software to generate new strategies. Well, I will not bore you with gigantic tables and a bunch of numbers, so I'll cut to the chase. Sentinel is better than random, as expected, so it passes the sanity check. For research question number 2 and 3, though, we have some interesting results. During the comparison to the other strategies, we found out that Sentinel is able to generate better strategies in 95% of the time with statistical significance. This is an example of the quality of the strategies. The graph here, what you're seeing here, in the y-axis, is the score of the strategies, whereas in the x-axis, you can see the relative cost of the strategy in comparison to the set of all mutants, so the execution time of the strategy. As you can see, the triangles are more scattered in this plot, meaning that Sentinel generates diverse strategies. Also, the strategies show a better trade-off between quality and cost, dominating almost all other traditional strategies. So what you're seeing in this curve here on the left top side is usually the region with the best trade-off between the strategies, and they are almost all from Sentinel. So if the engineer were to pick a strategy here, they would select one that is perhaps in this knee part, obtaining a relative cost of around 15%, while maintaining a score of around 90%. Now answering RQ3, we found out that these results hold for at least 3 newer versions of the software. In 95% of the version updates, the strategies can maintain their results with statistical equivalence. So, after answering the research questions, I'm going to outline here some of the benefits of using Sentinel. The first one is that, well, it performs your experiments for you. It automates the task of finding or creating a new algorithm, and it generates those algorithms with good results. Since the strategies are trained to be as cheap as possible, in the long run, they will save time. They can save as much as 90% of execution cost. Also, training is not necessary every time a new version of the software is released, thus the training cost is an acceptable price to pay for such good results. In the long run, this training cost is amortized by the good results. Well, since there is no such thing as free lunch, there are some caveats to this approach. Perhaps these limitations also apply to other AI techniques, so let's discuss them in a specific and then a more broad sense. The first limitation, as some can imagine, is the upfront cost of training, which is non-trivial and it's a challenge to overcome. This is true to almost any kind of AI training, be it in optimization or machine learning. However, this cost is usually still lower than manually experimenting with a set of strategies and hand-picking the best one. Sentinel also suffers the drawbacks of the fitness functions that guide it, especially the mutation score. Mutation score is not perfect, it bloats. Multiple papers have shown that a high mutation score of, let's say, 90% is easy to achieve because most mutants are too easy to kill and ultimately irrelevant. That extra 10% is where the gold comes from, but everybody knows that gold is very expensive to extract. Hence, we need better metrics than the current ones to focus our resources on the mutants that really matter. Finally, Sentinel uses a predefined set of components to generate strategies. It does not evolve the set of components, thus there is so much that it can do. One way of improving would be to automatically generate new mutation operators and include them in the loop while generating new strategies. Well, this concludes my talk. Thanks for watching. I'm open for questions.
Hello, everyone, and thank you for that excellent paper. I really must thank you, Giovanni, for the good
Thank you.
video and all the authors for the paper, which is a journal first paper. So we have a lot of good questions in the chat. I'll just quickly ask. It's an open source tool, I guess, Sentinel. It's a bit hard to find when you Google it. Could you help us on this?
Okay. Oh, thank you, Sigrid, for chairing the session and for the nice comments. And yeah, it's open source. And I think there is a link in the paper, but I'm gonna link here in the chat as well. So if you guys who are watching here now want to check on Sentinel, there is the preprint there as well, and the replication package, so you can check it out there.
Okay. So we have a lot of good questions here from Raul. So his first question is, isn't effectiveness or mutation selection about keeping the effectiveness intact, not the mutation score? And it's a long discussion, right?
Yeah, it's a long discussion. Yeah. Well, in practice, yeah. So basically, effectiveness as in number of unique faults revealed. However, we didn't have the information about unique faults in the software we tested Sentinel with.
Okay.
So basically, what proxy for effectiveness was the mutation score. So basically, in the paper, we say Sentinel the strategy generated by Sentinel maintain the mutation score when the mutants selected by the strategies require a test set that maintains the mutation score when executed on all mutants. So we get the test set, we execute on all mutants, and then we see the effectiveness of these smaller test set, let's say, that can exercise those mutants. So if we have a representative subset of mutants, then it's going to require good test cases. And we use mutation score to measure this. But yeah, mutation score is not perfect, but it's one of the caveats or one of the limitations of our work. Mm-hmm.
Okay. So another really important thing I think with the tool is that when you're going to try and adapt it to yourself, so when do you really need to retrain? Is it you need to do a lot of adaptation?
So basically, research question, if I recall correctly, research question number 3, right? We talked about this, and then we did some set of experiments. So we trained Sentinel on one version of the software, and then we used those strategies trained there and tested those strategies on 2 or 3 subsequent versions of the software. And in this regard, those strategies maintained their good results. So at least for those programs we tested on, and at least for 3 newer versions of the software, we don't need to retrain. So, well, testing and training, doing those experiments was very, very expensive. So it took us like 8 months to do all the experiments. Yeah, mutation testing is very expensive. So it took us an awful lot of time to run our tool and then test everything and then 30 runs and then thousands of strategies. So doing for more than 3 or 4 versions of the software, all our experiments was not feasible. But with at least 3, I can say that for the software we tested on, at least 3, you don't need to retrain Sentinel. You can reuse your strategy.
Okay. So there is also another question: how much change is acceptable before requiring retraining?
Yeah, good question. So we also showed in the paper a table with the code churn between each version of those versions that we talked about, and we have code churn from like 100 lines of code churn to I think 1,000. I have to check again the paper, but I don't recall correctly. But there is there's a wide range of code churn change, and the results maintain the same. I cannot really answer exactly this question. This was in our first plan to answer. So getting the first version of the software and then retrain up until the release. But quickly we saw that it was not feasible for the experiment. Then we could answer this question, but for now, we don't know yet.
Yeah, okay. So one of the limitation, I looked into the times in your paper, and you seem to have like the worst program was like 8 hours and so on to run. And of course, you understand the need of speeding things up a bit. But I mean, have you thought about, using more CPU power in the sense of parallelizing or speeding up in other ways? Because if this is, you say, if it's going to take so much time, it will be a hurdle to use in everyday development, right?
Yeah. So basically, this can be done. We use Pete, the mutation tool in our work, and then we used Pete there, and Pete has parallelization. However, because we were and then because we were trying to get the exact execution time for the execution time analysis, we disabled parallelism to disable any kind of noise that could be introduced. So that's why it took long. But yeah, it can be parallelized. And there are some other techniques as well that can be done, like checkpoints and I don't know, caching. We already do caching for mutant execution, but there are some other techniques that can improve and you can extend them. Yes.
And you have tried it on larger program, I guess. After the paper, it was a bit. It's been some time since you released it. You have run it on other.
No, I haven't. I haven't extended it yet. No.
Okay. So Raul has another great question there. If you're maintaining the effectiveness, then wouldn't the minimal mutant set be a better measure? This is a usual measure for effectiveness, or is what you are maintaining is essentially the minimal mutant set?
So the minimal mutant set, is it from the minimum mutant set from, I forgot the name of the authors, but if I recall correctly, is selecting the test cases and then doing the joint the disjoint set of tests and mutants. That's it. Exactly. Yeah. Well, we could use the minimum mutant set, yes, but then for the strategies are meant to be used before executing the mutants. So let's say in practice you want to use a strategy, you haven't executed any mutant, you don't know which test cases kill which mutants. So to find this minimal mutant set, you need the execution matrix of test cases by mutants. This wouldn't be practical for the strategy generated in this scenario that we're testing, which is using it before generating the mutants, before executing the mutants. But yeah, this would be much better. Yes, then we could compare with the minimal mutant set. For the evaluation. Okay. Yes, this is one thing that could be done. Yeah, we haven't done it, but yeah, for the evaluation we could have done it.
Okay, good expansion. Next paper, right?
Yeah.
Now it's only 30 seconds left. If there is anyone, still use the chat to post questions, and you can also go back in the discussion room that will be posted automatically. The next session will start. I will again thank the authors.